So keep on going now. So we're entering the third topics today. So far, as I mentioned, we saw just some very basic commands that allowed me to show you how to execute commands in containers, how to download them, how to open up shell. Now we still need some little pieces to be able to use containers to actually run any meaningful scientific analysis. And now we're going to cover a couple of important topics: how to share files between the host machine and containers. And there are special flags and special environment variables for that we're going to see quite soon. And also how to eventually tweak and tune the sharing of variables between host and containers. So let's move back to the terminal and just ask ourselves some questions. So first question, so we'll use again for the time being the Docker Ubuntu image, just because it's small and simple. We're not getting distracted by any extra functionalities or applications. So let's ask ourselves, what does the file system, so the collection of files in the container, look like? So let's have a look at the content of the root directory in the container. And we have this collection of files and directories. Now let's have a look, so we can compare with the content of the root directory in the host machine. And what you can see basically is that they're different. So in the container, for instance, you have this singularity item that is nowhere to be found here, and vice versa. In my host machine, there is a snap item, VM Linux item, and so on. So this is just to show you in practice that the file systems in the container in the host machine are two different things. And that's what allows you to ship your application in an encapsulated, independent, autonomous way through containers. Another question, so where are we in terms of current working directory in the container? And we can use the pwd command of Linux to get to know that. Okay, and where are we in the host machine? Same place. So this is an aspect of integration I mentioned before. So by default, a container will run and execute in the same directory that you were previously in the host. Can we see the content of this directory? Yes, we can. All right, so by default, again, the content of the current directory is available in the container, which means, for instance, I can create a file. Touch is just a simple way in Linux to create empty files. So if I create a file inside the working directory, I get to see it in my host as well, because the current directory by default is shared between host and container. This is quite good, but let's see. So sometimes in a lot of file system setups, you might have some pieces of software or data information that is not sitting right in your current directory, but it's sitting somewhere else. And then thinking, for instance, about genomics databases, which are often installed in a system-wide available directory on shared file systems. And so that would not fall inside the current directory. So can we see directories that are outside the current directory from a container? And say, can we see this directory inside the container? Sorry, this was just a type of me. I left touch there. So the right command is just ls to see if we can have a look at the content of the directory. Says no such file of directory. So maybe the directory does not exist. Is it maybe it was just me typing random stuff? No, the directory actually exists. So it has about 15 files in there, but we can't see them from the container. And that's because by default, the container will only share the current directory. So this can be an issue, right? We can't access by default these type of locations. Can we overcome that? So we can. So there is a flag in Singularity exec or Singularity shell that allows you to specifically and explicitly mount additional directories in your container. And so if I go like this, so after Singularity exec, I add -B and another directory. Well, I'm now able to see the content of that directory. And if I wanted to write files there, I could. So that's the way to make additional directories available inside a container. And it looks quite straightforward, isn't it? There is a small variation to this syntax in that you can even give the directory a different name if you wish to, and you can do that by adding a colon after the -B directory specification. And this basically means that you are now referring to that directory in the container with a different name. And I'm going to show you later a good user case for this syntax. Right, so getting the same result. And one last way to achieve this is by using an environment variable, which is called Singularity bind path. And basically you can feed the very same information there. And now you don't need the -B flag anymore. So basically it's a typing saver. If you know you need a directory basically often in your workflow, you can just define this variable at the beginning, and then you can save typing time later on. All right. One last thing on, so we now know how to make any directory we wish available in the container. A couple of extra comments. Never bind mount the root directory. So never do something like this. It would basically break the container, because then you would mount the entire host file system in the container, and then you would see an overlap of system files, system applications, and things would just not work anymore. So that's not a good idea. By default, at least in properly configured HPC centers, the home directory of the user would not be mounted in the container, and that's for kind of security reasons, especially if you are using the container to run web services, web sessions that might be accessed by third-party people. So the home often contains sensitive files, sensitive data, might be your SSH keys, other secrets that need to remain secrets in terms of the configuration of your access to that machine. So our suggestion is to always avoid mounting home. Do not do that. If you really need, there are cases where an application in a container needs some files in the home because that's the way it was designed. Well, you can always mount just a specific file from your home. Say you need a file in the home, you can just mount that one. So that way you are not mounting any sensitive data, you are just really mounting that single file or single directory that you need. Another way to achieve that, say there is an image that really needs a home, needs to write on that home, create new files and directories. Well, you can use, to that end, that syntax I introduced you before, where you are renaming directories between hosts and containers. So you can create a false home and name that false home as the real home in the container. So that's basically a trick, so that you make the home available in the container for the application that needs it, but that home is not your real host home. So there is no sensitive data there. It's just a service directory that you're using for the purpose of the application you're running in the container. So we could spend a lot of time and examples on this. Here I'm just giving you the basics of how to use this syntax to mount directories. Good. A couple of extra concepts that can be useful here. So let me go back to when I was just using directories in the container without mounting anything from the host. So here's just a quick question. Can I create files inside the container? So say in the containers root directory. No, gives me an error. It says cannot touch hello from root. And the reason is it's a read-only file system. So this is quite important, every container that is run by Singularity is a read-only system. So every directory and file that belongs to the container can't be modified. You can't create file, you can't edit file. The only files you can edit are the ones that reside in host directories, which is why it's so important to know ways of mounting and sharing directories from the host. That's the only way you can actually get a containerized application to actually produce some output, to do some work and save it for you to use later, all right? Okay. I think we have seen enough about sharing directories. I will just briefly mention, without examples, that, as we said, by default, you share the same environment variables between host and containers, which is good in a lot of situations, but there might be applications or cases where you want to that not to happen. So you want an isolated environment in terms of shell variables. And you can achieve that with a special flag, which is -C, that will basically cut out ties between the variables in the host and variables in the containers. And then if you still need to pass specific variables in these highly isolated containers, there is basically a Singularity syntax for that, which is defining variables in the host with this prefix, Singularity env _. I'm not going for an example today, but this syntax, I will reuse this syntax tomorrow in the second webinar in a nice example we're going to cover. So hold on to that, we'll get back. So now after we've seen how to run containers, how to share files with containers, maybe it's time to go for a practical example to give you the feeling that you can do some science for real with containers. So we're going to go for a science demo using BLAST, which I think needs no introduction to this audience. It's just a very, very popular tool in genomics analysis. So let me just move to the appropriate directory. It is ready for the purpose. So in this BLAST directory, we have a FASTA file, an input file ready for the analysis. And then in a separate directory, we have also a small database for BLAST that we'll need to use. But what do we need to achieve? Well, this is a very small example. So I've saved the protocol in this file just for ease of use today. We need to do a very simple thing, actually. We'll need to prepare the database for usage with BLAST with this command make BLAST db that maybe some of you have even used in the research career. And then after the database is ready, we'll need to run BLASTp to perform a search of sequence alignment between the FASTA file in this directory and the database file in the other directory. And we get that printed out in a nice output file. So we don't have BLAST installed in our system, as you see. So we want to use containers to this end. And so this would be a nice occasion to go on your web browser, open up key.io and look for a BLAST container. Just to save some time today, I've done it for you this morning during coffee time. And I've just saved the name of the latest version of BLAST from inside the key.io database of container images. So I'm going to use this guy to run this BLAST analysis today. So first thing, maybe we can just start and use the syntax we saw before. So singularity pool, just to make a local copy of the container image. It will run quite fast because I have pre-cached the image yesterday just to save some time today. So you can now see that we have a nice BLAST. So a nice BLAST image file here. We will need just some preparation in the BLAST database directory because the database is still compressed. So let's decompress it so we can use it. Yeah, and now I think I'm pretty ready to run the demo. So with this database, and we saw, let me just review the analysis we want to run. We saw, well, yeah, the first command is to make the database. So it takes as an input this zebrafish protein database. We want to make the database compatible with the type prot. I'm being a bit inaccurate here. I'm not a bioinformatician by training, so apologies. So let's give it a go. So we want to run this command in the container. So let's just use singularity exec, and we have just downloaded the container for BLAST in that other directory here, right? It was called, here we go, BLAST_290 and some string. And then let us just paste the very same command we would run for any BLAST installation, just as the command that we want to run in the container. And here we go. Yeah, it worked. So we just built the database using the containerized version of BLAST. You can see there are some extra files that appeared in the directory here. So the database is ready for usage. We can now go back to the BLAST directory where the sample input is. And so the next command we want to execute is the blast_p command. I will just copy paste here to save me some typing. So let's do the same. We want to run this blast_p alignment, and let's do it using the container that we just downloaded. So it will be singularity exec blast290 blah blah.sif, and then the command was blast_p the query sequence, and then the database location. Here I'm just using relative paths, so it's on the blastdb, the protein database, and our results. Do you think it will work? Database error. So what happens? It can't find the database. You might be surprised. You might not be surprised. Well, that's because I'm looking for a database that doesn't sit in the current directory. So here I need to use the host directory mounting syntax we just saw, say, no more than 10 minutes ago. So let me go back to this syntax, and after the exec instruction of singularity, let me add a bind mounting flag to bind mount the blastdb directory, and let's see how it goes. Right? So that is just a warning, but now we didn't get the error anymore. So did we get our output? Yes, that's it. So we just ran a very small sample BLAST analysis by using BLAST. There was no BLAST installed on my host machine. All I had to do was to download a BLAST container from key.io and use it. It's a time saver, isn't it? Yeah, open for a couple of questions.
All right, thanks, Marco. Again, a lot of good discussion going on in the Google Doc. One question, can I mount the external BLAST database to the Singularity, and how would I do that?
Yeah. So provided that the external database is available in the machine where you're running Singularity from, yes, you can. And it's basically the syntax you kind of just saw. So in our case, the BLAST database was in this directory. And so I used -b in the directory path to make it available. So now say you have a directory in your file system called data BLAST database, just as an example. Well, just add -b data BLAST database to your execution line, and that's it. Or if you want to just do it once and for all at the beginning of your analysis, you can just use the variable way of doing it. So export Singularity bind path and the path. One interesting thing here, so in the Pawsey file systems, we try and make the life even a bit easier for users. So Pawsey users might know that we have two key directories on Pawsey file systems, which are group and scratch. When you load the Singularity module on Pawsey systems, those two directories are bind mounted by default, exactly with this syntax, which means that everything that you might need that is found under those two directories is already available. You don't even need to care about mounting those directories because we have bind mounted them for you.
Okay. There is another question. It's kind of a clarification. So can you pass environment files with multiple env_vars to a container with Singularity? For example, with Docker Compose, I can load a .env file and the container will use its contents to set its environment variables.
Ah, yes, right. Unfortunately, so in the current Singularity version, unfortunately, you can't pass a single file with all of the definitions. And when I say current version, I think this is still the latest one, 3.5.3. But so Singularity 3.6 has been in beta version for like 2 months. And I noticed that one of the new features would be exactly that one. So you will be able to specify the variable, the mounting you need and variables you need in a single file and just provide that file. What you would do right now is Singularity, and I didn't mention that before. You can provide multiple mounting points by making a list which is comma separated. So this would work. If you need to mount 4 directories, say, you just make a comma separated list. And this would work the same with the -b syntax. So something like that.
Okay.
But I agree with you. I mean, being able to provide this list in a file and then just provide the file would be much nicer in terms of the user experience, and we are getting there.
Okay, thanks. Do you have time for one more?
Yeah, last question, maybe.
Okay, this is kind of taking it up a level rather into the coding. Reliability of pre-built containers.
Yeah.
How can you tell
yes,
if they're trustworthy?
Yeah, good question. So, good question. I mean, we have kind of discussed security before. What I can add here is will the container work or not? I mean, was the application built properly in a third-party image or not? So, well, that's why, to an audience of bioinformaticians, I recommend using the biocontainers project. I consider it kind of a trusted source. Because basically the authors behind are the same authors of Bioconda. They've been curating the list of Bioconda packages, thousands of packages for years now, and now they're just converted and made available the same tool set in containers. So to me, they're the most trusted source of biocontainers images. So every time I look for bioinformatics packages, if there is the biocontainers version, here I am back on my web browser in the key.io website. Yeah. If there is a biocontainers version, I will pick that one because I don't know the guys in person, but I know that the organization behind this project is quite cool and they do things quite well. You might still get some broken images, which means you run the command, it gives you an error. It happens to me with SAMtools, for instance. SAMtools itself works, but some other tools that ship with SAMtools don't. So in those cases, I just build my own image. So I ensure that everything is working as it should. A good practice that you might enforce is that when you download the image, you can run some very quick check. Say, can I run blast P from a blast container and get the output? Yeah, that's a good sign. I mean, if you can get the application to run a simple command, okay, there are good chances it will work. It might be more formal and even have a small set of input files that you can use for testing the containerized application. My take is that this procedure, even if you add this formal testing step with a small data set, it will still save you heaps of time compared to building the tool yourself. So it's well worth. And my experience, again, out of, I don't know, 10, 20 bioinformatics packages I'm looking for in biocontainers, maybe one is broken, the other ones will just work. So it's, to say, overall, the biocontainers project on Kit.io is quite robust, and it ships working containers.